Yeah, so we have the room from 6:30 to 8:30, and I think our plan is to start writing at 6:45.
What you can find on course link?
I think that was in an announcement.
An announcement.
Yeah, we should also put it in the actual little folder. Yeah.
I put everything in announcement.
Okay, 10 seconds left here. Great. I think 2 people answered in the 1 minute. Everybody else got it in beforehand, which is great. Okay. So this funny symbol, P, funny script P, A line B, what does that mean? We've been working with it for a while, but there's lots of different ways to say it. What did people say? Okay. Hoo-hoo, 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 hoo-hoo. Okay. Given A has occurred, the probability that B happens. This one is super common. You'll see given something, something else. So this given language is very common. And in fact, I sometimes read this line out loud as given. But nobody fell into my trap, which is that this one, I wrote it backwards, right? So this one is perfectly correct if you switch the A and the B. Given B has occurred, the probability that A happens, that is perfectly correct. Or the probability of A given B, also perfectly correct. So this sentence is, all the words are 100% right. It's just that the symbols A and B are in the wrong order, and nobody fell into my trap. Okay. The probability that A happens, if we know that B happens, almost everybody selected this one, and this one is also correct. You will often see this one with the clauses, the English language clauses. So this is what clause, the probability A happens. And if we know that B happened, that's another clause. You'll often see them in the opposite order. So someone will write down, if we know that B has happened, comma, the probability A happens. But you can write it in either order. This one is perfectly correct. The probability of A and B happening, nobody fell into that trap either. That one is A intersection B. A lot of people selected the conditional probability of A and B. 44 people. And that one is wrong. If you selected that one is wrong. Someone tell me what's wrong with the conditional probability of A and B? Why isn't that one right? Yeah. I think if you wrote just the conditional probability of A, that would also be wrong. So you need to have B on there somewhere. Maybe you could have it. So the thing is, when you're talking in the English language, sometimes people know what you're talking about already. So maybe there's a sentence earlier on that says, we are on the event B, or B has happened. And then it says the conditional probability of A, and it's understood that we mean given that B has happened. So that could happen. But if it was a sentence on its own with nothing around it, you got to include B somewhere. So you're right. The conditional probability of A, I think, could be correct if it is known from context that we're talking about B has already happened. But otherwise, B needs to be there somewhere. Yeah, so great thought. Anyone else have an idea? I saw one other hand here, maybe. No? Yeah. Yeah, that's right. So and is confusing because it means intersection. Sometimes and means union. So yeah, what does it mean here? Or how would you fix it, rather, maybe is the... Yeah, if you said given, the conditional probability of A given B, that would be great. That would perfectly fix it. The other problem with and is always symmetric. A and B is the same as B and A. This one is hiding the order, right? It's not clear if this means the probability of A given B, or does it mean the probability of B given A? And the order matters a lot. If you have the order wrong, it's a completely different thing. And we're going to see some examples of that today. But it's really important that the order is always there. So the conditional probability of A given B would be perfectly correct. The conditional probability of A when B occurs, that would also be correct. But you need to have some kind of difference between A and B. They cannot be symmetric. And just saying and does not tell you which one is which. So that's very important. OK. Any other questions or comments about that one? OK, we're going to see some examples where the order matters a lot. A given B and B given A are completely different things. That's why this one was completely backwards. And we're going to see in real life, this can really trip you up if you're not careful. OK, let's move to these more on this stuff, which is a big topic in the course. All right, Professor Humphrey, please take it away.
Could you people hear me? You could still hear me. OK.
When I started teaching here at Guelph, we didn't have microphones, so I just had to develop a fairly loud voice, even though I like to think I have a soft and gentle voice. Okay, on to our next thing. This is what we call a classic Bayes theorem example. And I want to give you a pre-warning on this idea. For some reason, people think Bayes' theorem is so difficult. It is so difficult. And many students solve Bayes' theorem questions without even knowing they're working with so-called Bayes' theorem. And so we'll look at sort of the characteristics, what makes something a Bayes' theorem question eventually, okay? So don't let that freak you out.
Actually, maybe I'll say the homework that you already did had what people would call Bayes' theorem questions already.
It's already had it. We just did one last day.
On the homework that was due on Friday with these questions like the prisoner escaping, and what was the other one? Oh, the flip your magical value when you flip the coin and roll the dice. Those were both Bayes' theorem questions, and you did them without knowing what Bayes' theorem is, which is exactly what we wanted you to do, and you did them all very well. So I think people did a good job on that.
And this was a Bayes' theorem question. And, maybe we'll see some more. There's lots of them in the practice questions, too. I will mention those practice questions. There's some pretty tough questions in there, okay? And the idea is that when you're training, you want to take it a little beyond what you would get on a test, so you're really ready to ace the test, okay? So don't get discouraged, work through things, and remember, collaborate, And we're not going to post solutions early because we don't want to get people into the thing of, oh, let's just wait till the solutions are posted, then we read the solutions. That is the worst possible thing you can do to teach yourself any kind of mathematical type subject, because the solutions always look so easy. But the question is, can you get your brain to go that way in the first place? That's a very different thing. So the thing is to work them on your own, compare them with your friends, see if you can come up with a consensus, and eventually we will give you some answers so you can check some of those out and see that you're on the right track. But we don't want you to just wait for solutions. Get those going quickly. Okay, so on to our next thing here. So this is a very famous example. It's a classic example, what we call the rare disease example. So we start with the premise that a rare disease strikes on average 1 in every 1,000 people. Okay? 1 in 1,000 sounds pretty rare. There are lots of diseases which we are scared to death of, which are much less common than 1 in 1,000. 1 in 1,000 is fairly common for a rare disease. A test exists for diagnosing the disease. And if a person has the disease, the test is positive 99% of the time. In other words, if you've got the disease, it's going to tell you you have the disease with probability 0.99. This is a very, very good test. And if the person doesn't have the disease, it'll come back and give you a negative 98% of the time. Okay? So that's all the information we really need here. Now, you get tested for the disease. Kind of consider yourself kind of like a ball in an urn being selected out of the population. You get tested for the disease, and your diagnosis is positive. And so what we want to know is, what is the probability you actually have the disease? Okay? Now, you've got a positive. This is a horrid disease. Weird things break out all over your body eventually, and we don't even want to say where it goes after that. So it's a terrible disease. You can think about how depressed you would be with this positive diagnosis. Anyhow, what I would like you to do is give us a
So there's some buckets. You can say less than 10%, 10 to 30%, 30 to 70%, 70 to 90%, or more than 90%. What is the chance you have the disease in the situation we just described? So you've tested positive. What is the chance you actually have the disease? Okay, we'll give you 1 minute. Give us your gut feeling. So you're at the doctor's office, and you're trying to figure out if you have the disease or not. Okay, let's see what people chose. Okay, very nice split. So out of 60 people who voted, 32 people said greater than 90%. This seems very intuitive. And in fact, this is the option that many medical doctors will choose. So medical doctors are also given these questions, and they often choose things over 90%. Then it's got a little smattering over here. 11 people, a little bit less likely. 5, 6, and 7. The correct answer is less than 10%. If you chose less than 10%, you got it right. Even though this test is very, very accurate and you have received a positive test, your chance of actually having the disease is still quite small, less than 10%. What is going on? This is extremely counterintuitive.
In fact, it's less than 5%. It is less than 5%. So that's what we will sort out next. Why is it under 5%? Okay, let's see. So what do we need to do? We need to go back to this. Okay. So again, put this up, and you've done this on Mathematized, but again, the idea is that intuitively people tend to guess that it's going to be a high probability, whereas in fact the answer is a very pretty low probability. So what we need to do is attack this question and start off with defining events for the question. And solving a probability question with words, this is actually one of the trickier things to do, is to think of how you define your events, okay? So what we have to do is think of, okay, a person either has the disease or they don't have the disease. And then they either test positive or they don't test positive. But a person with the disease can either test positive or test negative. A person without the disease can either test positive or test negative. And so what we want to do is separate as events whether or not they have the disease and whether or not they test positive. Okay, those are kind of like two things that we want to separate. Then our next thing is, looks like you've got an exercise ready to go here. Is to ask yourself, what are we trying to find and what probabilities are given in the question? Okay, so what are we trying to find? Let's see, I want to go to a dot camera on this one. Dot camera on this one. Got that dot camera. And we're also going to ask probabilities given in the question. Q, short form for question. Okay, so we have the disease. There's the A has the disease, B that the person tests positive. So we go back and let's take a look and say, what is it we're trying to find? You're tested for the disease. Your diagnosis is positive. So what we conditionally know is that you've got a positive test. What we don't know for sure is whether or not you have the disease. So we know that you've got a positive disease. That is the condition. And testing positive for the disease is B. So we have the condition of B, and we're trying to find the probability that you have the disease. So we're trying to find the probability of A given B. Okay, so let's now go back and ask what probabilities are given in the question. A rare disease strikes on average 1 in 1,000 people. A is the event that a person has the disease. So we'll say the probability of A is 1 in 1,000. And if I get my decimals right, I think that's 0.001. Now, we've also got other numbers in there. If a person has the disease, the test is positive 99% of the time. If the person has the disease, well, that is given A. And so then the probability of testing positive is 0.99. What else are we given? If a person does not have the disease, the test is negative 98% of the time. So we are given that if they don't have the disease, that's a complement. That goes after the complement symbol. The probability that they don't have the disease, so that's probability B complement given A complement, that's 0.98. Okay, so now we've got some good information. Now, one of the things I'm going to point out is what makes this a classic Bayes theorem question, okay? The classic Bayes theorem question really comes to me in that we want to reverse a conditional probability. We have the probability of B given A. I want the probability of A given B. That's what you watch for. And we're going to use a little trick to make this kind of an easy question. I think it's an easy question. And here's the other thing I'll say is people who attack this with something like a probability tree or a Venn diagram or Venn-like diagram, squares are nice, rectangles are nice, that kind of thing. They often intuitively get to the answer without even recognizing it as Bayes' theorem. They just kind of intuitively work through everything, and you get your answer. So let's now do a probability tree. And we do this on paper. I do not put it on a slide. To work through the probability tree, we want you to kind of like think it through. Think it through. Okay, so here's our probability tree. Probability tree, sorry, not probability true. Probability tree. Okay, so we start off, and our first question is, do you have the disease? Yes equals A is event A. No is event A complement. And now we're going to attach probabilities to this. And this probability was 0.001. That was the 1 in 1,000. So that was the probability of A. And so if 0.001 is the probability of A, the probability of A complement is 0.999. That's the probability of A complement. Okay. Now, the next question is test positive. Well, not no. Let's say start off with yes. Yes. A yes is a B. Okay. So I'm going to draw my line saying that's kind of a little tricky here. Get my, I guess nobody said the branches on a tree have to be perfectly straight, right? So we'll kind of go like with this. So we've got B, and we've got B complement. If you have the disease, you could test positive. And the probability of B given A, that was 0.99. And again, that is the probability of B given A. Okay, so if the probability of getting a positive test if you have the disease is 0.99. The probability that you don't test positive is going to be 0.01 if you have the disease. And so that is the probability of B complement given A. But if you didn't have the disease, you could still test positive. Or you would expect that if you don't have the disease, you're likely to test negative. Well, that's true. In fact, the probability of B complement was 0.98 if you tested negative. And that is, what is that? That is the probability of B complement given A complement. So if that's 0.98, notice the probability of B given A complement is B given A complement. That is just, it's the complement is B given A complement. So this probability is 0.02. That's the probability of B given A complement. So the idea is that given you're in the restricted sample space of A complement, either B occurs or B does not occur. Okay, and this is something that you watch for. Given that you have the disease, you either test positive or you don't test positive. If you don't have the disease, you either test positive or you don't test positive. So B, got that. So we can now go through and get all of our intersections. And, sometimes I say I wish I'd left myself a little more space on the right, but that's okay. We're going to go through and get these intersections. And so first one is the probability of A intersect B. I'm going to take the probability of A times the probability of B given A. And I'm going to write it out here. This one and so I'm going to take 0.001 and multiply it by 0.99. 0.09. I'm not going to work out the number right at the moment. And then this one is going to be the probability of A intersect B complement. I'm going to take the probability of A times the probability of B complement given A. And if you're having a hard time reading my writing, just think it through, okay? Ask yourself, what should I be writing down? Don't just say, what am I copying? Just say to yourself, what should I be writing down? And actually, let me I'm just going to have you just spend a minute, just go ahead and write out what the next two intersections as well. Just fill those in. We'll just double check that when I go through them that you're getting what I want. And in fact, what I'll do is I'll just freeze this for a moment so they can't see me writing. Nobody can see me writing. Oh, did I not freeze it? Oh.
I think one of them doesn't freeze.
Which one doesn't freeze?
Let's hear. We'll put the problem back.
Okay.
There you go.
That'll work, something like that. Okay, I'm just trying to get it so that you can't see what I'm doing while you are just doing it ahead on your own. Ba-ba-ba-ba. went off the page. better redo that one again. And now I am ready to reveal. I'm ready to reveal. I'm ready to reveal. Okay. Looking good. Did I make any mistakes there? Everybody get what I got? Did you write down what I had? Did you write down what I had? Had it? Had it? All good? Any questions so far? Any questions there so far? Okay, so a bunch of numbers to calculate. Bunch of numbers to calculate indeed. So what we're going to do is I'm just going to go to the HDMI laptop. HDMI, which one do I want?
That's the one.
That's the one. I want that one, right? Okay.
You wanna leave the...
I can leave that one up. Okay. Not worried about that one. That's what I want. So we can fill in this table of probabilities. Okay. Again, now we're going to the idea of the 2x2 table. The idea being that we've got these four intersections. The four intersections are both mutually exclusive and exhaustive. Okay. We've got all four of our possibilities.
What does exhaustive mean again? Is that when it's like really you're really tired in the morning?
You're really exhaustive. So the idea of exhaustive is there are no other possibilities other than these four intersections. You got to fall in one of those four intersections. You're going to fall in one of those four intersections, and you can't fall into a gray zone unless we allowed for that gray zone, right?
So what does it have to do with being exhausted? Why is it?
So that would mean that our sample space, for the probabilities of those intersections, are going to sum to 1.
But it has nothing to do with being tired. This is my point. This is a bad name.
We have lots of bad names
Okay.
in math and statistics.
I think it's
let me get on to a couple of them. Well, no, that would be I can go on to some terrible ones.
I think it's like you've run out of possibilities. You've exhausted. There is all the possibilities were like your energy in the morning, and we have all the possibilities. We've just used it all up. There's none left. That's it.
Exactly.
Okay, great.
Now we might actually ask why a car has an exhaust system. Does that mean we're tired when exhaust goes out?
Yeah, that's also badly named.
Oh, another badly named one.
Yeah.
We should make them change all the names of exhaust systems
Yeah, I agree.
to something like. Okay. Anyhow, so we got these table of probabilities, and we could go through and fill them in as intersections. These are all pre-posted for you, right? And I will be posting after class sometime later today. I will be posting these slides again with just a couple more things added, which you will see in class today, but I didn't want in the pre-post. And if we think about that 2x2 table, we could put the marginal probabilities, marginal sums there. Coming down this way, the person has the disease, that's the probability of A. Don't have the disease, probability of A complement. You see that the probability of A is the probability of A intersect B plus the probability of A intersect not B, okay? Again, just a very standard thing when you talk about any event, and then you've got some other kind of event. Well, is either going to occur with that event or the complement of that event, or you could actually break that other event up into more than two pieces. Sometimes it's like a B1, a B2, B3, etc. And then this one here, that adds up there, or going across here, testing positive, person testing positive, yes, B is going to be the sum of the probability of A intersect B plus the probability of A complement intersect B. again, B either occurs with A or it occurs without A, summing to the probability of B. And we have just worked out all the numbers we need to fill this in. So we're just going to ask ourselves, how to make sense of what we have just seen with our tree. Well, I said we will do this on paper, but we have done this partly on paper. We've gone through and got those intersections. And let's see what else we've got. We drew our probability tree. And we arrived at a final answer. Well, we're going to arrive at the final answer. So let's work on working out that final answer. First of all, let's go back. I kind of wish I'd put this one slide in a somewhat different spot. That's on there. Give me a freeze on this one for a minute. I got my slide in a. I got my slide in a spot I don't want it in. There. That's what I want.
Oh, okay.
Yeah.
You're good now. Okay.
Okay. I put one of my slides in a spot I didn't want to be, so I'll kind of reorder this when I do the final post here. Just a sec. Where am I? Where am I? Okay. Okay. Let's go back to this one. Simply going through, we can work out all of these probabilities. And so now I'm going to go to the dot camera. Is the dot camera live right now?
It is over there, yes.
It is over there. So let's just see what we did. A intersect B came out to 0.00099. And this one came out to, that's A intersect B complement. My goodness, how many zeros is there there? That's kind of like blow my mind. After the decimal place, 4 zeros and then a 1. And then A complement intersect B, the probability was 0.01998. And this one here, 0.97902, 0.97902. And if you add up those probabilities of those intersections, it should come out to 1. There might be a little bit of rounding error. I don't think in this case there's any rounding error. Okay, so we got that. So we're trying to find the probability of A given B. Okay, let's think about it in terms of this probability tree now and say, okay, A given B. B has occurred. B occurs here, and it occurs here. And so if we consider B could occur here, or it could occur here. Can't occur here, can't occur there. It can only occur in one of those two intersections. And then that becomes, in a sense, our restricted sample space, of which the only place that A occurs. Huh?
Would you like the scissors, Gary, or should we
No,
just
not my
the
beautiful
okay.
sheet.
I was so excited when I thought of cutting paper with scissors.
I know you were.
All right, I'll put it down.
Okay. So A occurs in one of these two spots, but the only spot, B occurs in one of these, in this intersection or this intersection, but the only one of those intersections where A also occurs is this one. So we want that one. So what did I do? I did something. Okay. So this is where I want to be on this one. Yes, this one. So we'll put this one on this. Maybe take that one back one. So let's just take a look at what we did. The probability of A given B. we take the probability of A intersect B over the probability of B. How did I get the probability of B? I summed the probability of those two intersections, the 0.000099 and the 0.01998. Okay, so ask yourself, where did we get that 0.02097? We'll go back to our key intermediate steps. Is that we got the probability of A intersect B by taking the probability of A given B given A. We got the probability of A complement intersect B by taking the probability of A complement given probability of B times the probability of A complement. And then we obtained the probability of B as the sum of these mutually exclusive intersections. And that's where we go back to that slide again. Got to think my arrangement of that one. We took that one plus that one, and that gave us that. And so our answer, A given B, was simply this value divided by the sum of these two values. In other words, this value divided by this marginal total. Okay, so that was one way to make sense of this. We drew our probability tree. But here's another way to make sense of the example. And in some ways, this is kind of more compelling to kind of try to make sense of why does this work this way. And consider a population of 40 million people, okay? I used 40 million because it's approximately, to the nearest 10 million, the population of Canada, which I double-checked as of 2024 is 41.29 million, which is a lot of people.
That's more than I remember it being.
I remember it always as 30-some million.
Yeah, that's how I remember it too.
I know. I remember when it crossed into the 30 million thing. And
I
that
don't-
wasn't
I
that
don't
long
remember
ago.
that.
I don't. You were born.
I only moved to
I
Canada.
think you
when
were
I
born. I think you were born.
But Canada was a foreign country to me until I was like 12.
Okay. Anyhow. And you weren't keeping track of the
No,
population
I wasn't of all the
census.
countries. I only kept track of one or two.
Yeah. Okay. Anyhow, that's where I'm going with 40 million. Okay. So that's what we're going to do. And so we'd say, how would well, it says 30 million, but it's 40 million. I updated it to 40 million. Okay. How would 40 million people be distributed? So we could go through there, and I got to get. Oh God, that was not.
Are the numbers missing?
No, they are there. Oh, maybe I left them out on purpose. I bet you I did. I did. First of all, that should be 40 million. 40 million. What we want to do, what we'll have you do, is go through and take those probabilities, take these probabilities, and multiply them each by 40 million. Okay? In fact, how much time we got? Have we got time to do that? I probably could do that. We'll do that right now. 40 million. So we got oh, you're working them out pretty fast.
Yeah, the secret is to not care about being accurate.
Oh, I want to be accurate.
Well, let's see who's faster.
I'm going to be very anal about this. Very anal. Let's see. 40 million. Two. Times 0.00099 equals 39,600. That comes out to 400, and that comes out to 40,000. And so this is going to come out to $39,960,000. And this is going to come out to well, it's certainly not going to come out to a negative number. What'd you come up with? About 800,000. About 800,000. But it's going to be. Is it going to be 800,000? God, I did a. There.
800. Yeah, that could be right. I
Could
don't
be
know.
right.
I thought it'd be a little less than 800,000.
If I'd be a little less.
Someone
than-
yell
yeah.
out what you got for this box. Did anyone do it more accurately than me? 99200. See, this is why.
Yeah.
This is why we keep students around.
Got that one. So let's see if we're going to do that one. Let's see how our time is. Oh, we're still got a couple minutes. Let's get this number exactly right.
Who got?
I
what
want
did people
that.
get for this 39.2 million number? Anyone? So 39 million. How much? How many hundred thousands? 160. Okay, perfect.
160,800.
Okay, so this is actually pretty good.
Get 800, right? Okay. Then we're going to add 400 in here. And that's going to give us 39,106,1200. That should add up to 40 million. And this group here is 799,200 plus 39,600.
So what is the punchline? Is that there's 40,000 people who actually have the disease and tested positive, but there's almost 800,000 people who don't have the disease but did test positive. So when you're given that you're one of this group, you are one of 840,000 people, but only 40,000 of those people actually have the disease. So that's why most of the time, most people who test positive will actually not have the disease.
Yeah.
I will add one more thing.
We'll go over the, we're going to go over the implications of this a little bit at the start of next lecture. So kind of look over the example, and I'm going to be tossing a couple extra slides in there.
I also did make an animated version of this problem. It's like a short 10-minute version. So if you want to check this out, in that one, the numbers were cooked a little bit differently so that there's only 1,000 people in the population. One person has the disease. 1,000 people don't have the disease. And then they should get hats. Yeah, there we go. They got hats. So some of them have positive hats. Some of them have negative hats. Basically exactly what we did today, but the short version.
The short version.
All right, we'll see everyone on Wednesday.
Okay.
There you go.